All right, what if we're given another simply supported beam with a distributed load to the middle here, of 20 kilonewtons per meter and an additional point load in the middle of 100 kilonewtons. Let's add some distances on here of 3 meters and 3 meters. A and B. We are also told that the material is made out of steel and VC must be less than or equal to 10 millimeters, where C is in the middle, once again, just like the last one. I want to find the required moment of inertia. All right, so a little bit different perspective. This time we're given the deflection, vertical deviation, VC, okay, as less than or equal to 10 millimeters. We're given the load, we're given the material. Now, what cross-section do we need? So this is a little bit more beam design. Okay, again, using Appendix C, we still have the point load in the middle, but we also have distributed load halfway. All right, so my solution is going to be my simply supported beam with the load halfway, 20 kilonewtons per meter, A, C, and B, plus my point load in the middle, A, B, and C, 100 kilonewtons, has to be less than or equal to 10 millimeters. All right, and again, I like to kind of draw the elastic curve. So this is going to bend down this way, and this is also going to bend down this way. So I'm looking at this deflection, VC2, and this deflection, VC1, has to be less than or equal to 10 millimeters. So of course, worst case scenario would be equal to 10 millimeters, right? All right, so looking up here, VC is in the middle of the span, which is going to be my maximum for the point load. And looky here, this deflection gives us two options. One of them is the maximum and the other one is the deflection at L divided by 2, which is where we are. Yay! So those are the two equations that I will be using. Negative 10 millimeters. Wait, why is it negative now? Because it's deflecting downward, right? So I've got to put that direction in there. Is equal to, okay, distributed load, negative 5 times W, 20 kilonewtons per meter, times length to the fourth, 6 meters to the fourth, all over 768 times E, 200 gigapascals times I that we don't know, minus load P, 100 kilonewtons, times the length cubed, all over 48 times E times I that I don't know. All right, I have kilonewtons, meters, and gigapascals, and millimeters. Okay, so a little side note, gigapascal is equal to a kilonewton per millimeter squared. So that means I can have 1,000 millimeters per meter to the fourth and 1,000 millimeters per meter cubed. And now everybody is in kilonewtons. Oh, I only need cubed here because one of those cancels out. I apologize. Cubed. And then that one cancels with that one. So now I have everything in kilonewtons and millimeters. All right. And I find solving for I using some fun algebra, we get 3.094 times 10 to the 6th millimeters to the fourth.